about various characterization tools which a dental student and a dental researcher can use during your research and in your thesis. So I understand that most of the audience here are UG and PG students and also faculty. Some may be clinicians who are very much interested in the research. So I wanted to share what all I have understood and I have used in my personal research in developing various materials for dental applications and also bone applications. If you're not audible anywhere or if you're not able to clearly understand, please stop me wherever you feel. And I'm actually a dentist, and I was interested very much in developing newer materials for dentistry. Then I studied nanotechnology, and I developed various nano materials for dental. And I have developed various materials for dental applications and as well as bone regenerative applications. And throughout my PhD, I was concentrating on developing new materials which are injectable and self-setting, which can be used for endodontic as well as periodontic applications. So I have used various material characterization techniques in my research, and currently also I am helping, and I am helping my students and also other students who are pursuing their UG and PG research in using these material characterizations. So I want to share my experience in my research with you all. So why this material characterization or these analytical tools are important? In all our research, when we are focusing on the dental materials, we are always interested to develop a new composition or to improvise an existing dental material. It may be a composite, it may be a polymer, it may be a metallic material, whatever it is. We want to improvise the properties. We want to improve every day. We want to improve. We want to customize. We want to adapt to our requirements. So every day, newer technologies and newer materials are evolving in dentistry, and dentistry is a very, very, very fascinating field. We can see that every day new advances come, starting from the imaging, starting from the diagnosis, starting from the treatment. In every field, we have newer materials coming in. So when we see newer technologies and newer materials coming in, we have to understand how these materials are going to interact in the human body, how these materials are going to affect or improvise or behave in the in vivo body environment. So for these things, various analytical tools are available, and it is important for a researcher, for a dental researcher, to first know what are all the tools which are already available. So there are who are doing your PG MDS, you should have already come across few of these equipments which I am just showing in the screen. So most of you must have seen in your research articles, people are using X-ray diffraction method. They are using FTIR, they are using electron microscopy, they are using transmission electron microscopy, they use ICP, they use UV spectroscopy, particle size analyzer, etc. And actually, this is not an extensive list. The list will never end. Actually, the material characterization techniques or the analytical techniques is not, it cannot be covered in a single lecture, and it needs a full 6 months course to cover it. So I will try to stick on how all you can use these analytical techniques in your dental research. So, so I will start one by one where all you can use it. So basically, you all in your dental materials course, you should have understood what are all the different types of material already exist. Like the materials can be classified. It can be classified as, simply a material can be classified as a crystalline material and a non-crystalline or a glassy material. These are the two types of material that exist in the nature. One should be a perfect crystalline structure, or it should be a amorphous or a glassy structure. So we all know this. All the materials falls into these two categories. Either it should be crystalline or amorphous. So when we take off crystalline, all our metallic materials all the ionic forms falls under the crystalline category. However, these polymers, most of these polymers, these resins, whatever you are using in your clinics, all these comes under the amorphous category. So first, when you start developing a new material for your research, it can be a dental cement, it can be a metal implant, it can be a composite, it can be for imaging applications, a diagnostic application, you are developing a quantum dot, a nano dot, a drug delivery solution, a tissue engineering scaffold, whatever research you are going to start with, in whatever departments you are. Okay, so you have to first understand what is the material you are going to now take in your hand and use, whether it is going to be a polymeric material which is amorphous, or whether it is going to be a crystalline material like a metallic material which is going to be crystalline. So you have to first understand what is the material, and then you have to decide about the characterization technique, what you are going to use or to study that particular material. The most affordable and the most easily available characterization tool which most of our dental materials will require is X-ray diffraction. So X-ray diffraction, as the name indicates, is a diffraction technique. So you all know how a X-ray machine will work. I need not teach you about that. You should have. You all are experts in that. So it's a normal X-ray machine, X-ray producing machine. The X-rays will come as a collimated rays. There is a parallel rays. It will be directed to the sample. If the sample is going to be a crystalline sample, okay, you take a crystalline sample, maybe a metal, you think it is a metal, or you think it is a hydroxyapatite, whatever it is, it's crystalline. So when a crystalline sample is placed, the crystalline sample will have the atoms arranged in the crystal planes, the exact crystal planes, so that when the X-rays falls on the crystal plane, it will get diffracted from each plane. Okay, and it will produce a constructive interference. You would have all read about the constructive interferences in your schools, right, in your physics. So it will make a constructive interference pattern. So this interference pattern will have peaks at different angle. So the X-rays has to be projected from 0 degree to 180 degree. It can be projected from 0 to 180 degree, but usually in our research we use to project from 0 to 60 degree or 70 degree depending on our material and where your peaks of that material stands. So we will project the X-rays onto the material, and then you will get the peaks, the diffraction pattern, which will be converted into a digital signal where you will see the peaks in the screen. So here you can see an image where you can see the peaks of a material. For example, I have shown here a zinc oxide material. So each of these peaks will correspond to a particular crystalline plane in the material. So you will be able to perfectly find out what is the material you are studying. Okay, so first this X-ray diffraction method will help you identify what is that sample. And from these diffraction and the peaks, you will be able to also calculate the distance between each of the crystal planes also. So like if you are making a quantum dot, okay, so the quantum dot, you may have added impurities in your quantum dot to enhance the imaging resolution of the quantum dot. So there may be variety of kinds of research. So when you are doing those things, the crystalline structure and the dimension of the crystalline planes will expand or constrict. So all these things can be studied when using these X-ray diffraction patterns. There are actually dedicated softwares like expert high score, read wheel refinement analysis, which can be done where you can compare this the pattern which you have received to the existing pattern. Already there is a library of XRD patterns which are already stored in these softwares. You can compare what X-ray diffraction you have got for your sample with the already existing library, and you can understand the differences in the spacing between each of the crystalline plane, and you can understand how much your crystal plane has expanded or it has constricted. So all these kinds of measurements can be easily done in this thing. So this is for a crystalline sample I am telling. So in the crystalline samples, you have definite crystal planes. You are getting a very good crystal peaks in the graph. What happens to the amorphous sample? So when it is an amorphous sample, you are taking. So many of the students who work on polymers, they also read papers, research papers and articles, and they may sometimes not understand that a polymeric sample is an amorphous sample, and they may go for a X-ray diffraction analysis. They may not get that much details in a X-ray diffraction analysis for an amorphous sample. A amorphous sample will always have just a flat kind of a graph. You may not get a exact peaks to identify what polymer it is exactly, whether it is a PCl polymer, whether it is a PLA polymer, whether it's a methacrylate polymer. You won't be able to find what type of polymer it will be, because polymers are mostly amorphous and they may be semi-crystalline. So whenever the polymers are semi-crystalline, you may be able to find one or two peaks. When it's going to be amorphous polymer, completely you are not going to find any of the X-ray diffraction peaks in your amorphous polymer. So what are all the advantages when you are using this X-ray diffraction method? So X-ray diffraction methods are, like as I said, it is a very, very affordable technique. So whenever you take your material for characterization, first you start with X-ray diffraction method. For crystalline samples, you can just start with X-ray diffraction method, because it will give you exactly, you will be able to identify exactly what is the material, if it has any impurities, or if it is a combination of two materials. If it is a combination of two materials, what is the percentage of each of the material? So all these things can be easily calculated and found only with a simple XRD, which may cost around some 300 rupees to 500 rupees. So always start with the X-ray diffraction analysis for your newer samples which you are creating in your lab or in your clinic. So next analytical tool which I'll be discussing is the Fourier transform infrared spectroscopy. So here also this is a very, very affordable characterization technique. Most of the material developers among you will be using, because you will need only a very small amount of sample. A pinch of sample is enough. And then in this method, you will be using infrared rays. So in the infrared rays will be passing through your sample, and mostly the molecular bands or the functional groups present in your sample will be analyzed by the Fourier transform infrared spectroscopy. This method is applicable both for crystalline sample or amorphous sample, because it is going to just see the functional groups. Mostly amorphous samples, if you are having any polymeric samples, you can just use Fourier transform infrared to identify what kind of polymer it is and what are all the functional group it has. If it is a blended polymer, if it is a copolymer, if you are using a combination of polymer, and if you are going to use a composite where there is a combination of a polymer and some other substance like a metal or a carbon fiber, whatever it is, when you are going to take such kind of sample, graphenes, so all these things, Fourier transform infrared will give you a very, very good spectrum, where you can understand what are all the molecules and the molecular functional groups that are exactly present in your sample. So here you can see how the samples are usually placed in a Fourier transform infrared spectroscopy instrument. Just a pinch of sample is enough. So sometimes the sample needs to be pelleted. You have to make it into a thin pellet kind of thing, through which the infrared light is going to pass through. And then there will be a detector. The detector will convert the analog signals to a spectrum, and you will see the spectrum. So for example, an infrared spectrum will just look like this. So The infrared wavelength will be usually from 4000 to 400 centimeter per centimeter, and then you will be able to see the peaks at each particular wave number. You There are plenty of research articles which are showing if a peak exists on one particular wave number, what will be that peak corresponds to. Like a OH peak will always exist around some 3000. Yeah, oxygen peak will always exist around 500. So such kind of library is already existing for your FTR spectroscopy. So if you are using a organic sample, okay, a plant derived sample, a polymeric sample, also for inorganic materials, just you can try this FTR method with just a pinch of sample to identify whether your sample is pure, whether it has any combination of different molecules in it, all those things. And even especially for drug delivery to identify particular drugs and how the drug is binding to the drug delivery vehicle, whatever you are using. So that kind of identification of the drug and the type of bonding can also be found using your Fourier transform infrared spectroscopy. Also, I have to mention here, like when you are using, for example, in drug delivery, when you are using a drug which can be bounded to the carrier, okay. So if the drug is having a particular ketone group, so the ketone group can get open up and it can bind to the particular functional group which is present in the carrier vehicle. Okay, so in that condition, what happens when there is a binding happens between these two materials, that is when the drug and the carrier, that particular functional peak will be missing in your spectrum. So with that inference, you will be able to identify that this is the exact type of bonding which is happening between the two materials, that is the drug and the polymer or whatever it is. This is, for example, I am telling like this for when you are developing a copolymer, when you are developing a blended polymer. So whenever you are doing all these combinations, you can identify what kind of a chemical interaction is going to happen between the two materials using the FTR spectroscopy. And the next is the scanning electron spectroscopy, and most of the PG researchers among you should be using scanning electron microscopy in your research already. I think so. So the scanning electron microscopy, many will be actually as students. When I was also as a student, I was very much interested in doing this scanning electron microscopy for a new sample which I developed. Like I just make a sample, I just do it, take it out of the furnace, and I will be very much fascinated how the sample will look and how it is in the microscopic level, that is in the nanometer level. I will be very much interested to know what it is. So we before doing these basic characterizations like XRD and FTR, I may jump into go and take a scanning electron microscopy, because you know how the scanning electron microscope images look. It's very fascinating. The electron microscopy instrument itself is a very fascinating instrument, and we all will be very much interested to see that material details. But always understand that the scanning electron microscopy will only give the pictures of the material. It can only give a magnified image of the material. It cannot identify what the material is. So you may be having a polymer sample in your hand. You may be having a ceramic sample in your hand. Okay, it may be a metal. But a scanning electron microscope cannot identify what it is. And without identifying what the material is exactly, you cannot proceed like how we are going to go with the scanning electron microscopy. Like for example, I will just slightly go into the principle of scanning electron microscopy so that you can understand what I am planning to tell. So in the scanning electron microscopy, unlike your optical microscopy where the light is used as the incident rays, here you can see the electron beam is the incident ray. Why we are using electron rays? Because electrons have a very small wavelength. okay, compared to the light, the visible light spectrum, where the wavelength ranges from like 200 to 800 something. Here, for the electron, it will be even more smaller. The wavelength will be even more smaller. Wave is even more. The resolution of the image produced by it will be very, very high resolution images. And again, I'm telling you are using electron source. So when it is an electron source to fall onto your sample, the electron is nothing but it's like a electricity. It has a charge. It has a power. Okay, and your sample, if it is a non-conducting sample, it is not going to take up this electron source. It is just going to accumulate the charges in your surface, in the surface of the sample. So when you are using a electron microscopy and you are having a non-conducting sample in your hand, you will encounter a lot of problems when you are getting the images, just like the charging which happens in the surface of the sample. So, for example, if you are having a polymer, which is going to be a non-conductive polymer, obviously polymers are not conductive, or if you are having some organic materials in your hand, which are going to be non-conductive, the electron source is not going to image your sample. The charges are just going to accumulate on the surface of the sample and you are not going to get a clear image. So what you are going to do here, because mostly more than 50% of the research, we are going to, all our dental colleagues are going to use non-conductive samples. So what we are going to do? We have to make the sample conductive. So to make the sample conductive, what we will do? We will coat the surface with a conductive material, like a gold, a plasma coating by gold. So when a gold thin layer of gold coating is given on your sample, it can be gold, it can be platinum, whatever it is, but gold is the most commonly used material for coating. Just in a very, very, very nano thickness, it can improve the surface conductivity of the sample. So here you can see various images taken from the scanning electron microscopy. So most of these images are of non-conductive samples, like some organic samples, cellular structures, plant samples. Many examples I have just randomly taken from internet and I have put. So how they are how you are adjusting the contrast of the image to get a good to get a good image is, you have to adjust the voltage properly, the current properly, and then you have to use the gold coating technique. Unless you have a conductive coating which is about 0.5 to 3 nanometer thickness, you won't get a good image. If you are using a metallic sample, like if you are developing some material for orthodontic applications, or you are developing some material as a dental implant, or you are developing materials for fracture reduction, um, some metallic material, maybe stainless steel or titanium or tantalum or whatever it is. So these kinds of materials are conductive. All the metallic materials are conductive, and they are good. They will be giving wonderful images without gold coating, and you can go even to very, very lesser size details. Like you can go even below 2 nanometers. When you are having a non-conductive sample, you may not go to that much less the high resolution image, that is to that much fine nanometer details. You may stop only till some 1000x or 5000x or 10,000x. But if it is a conductive sample, you will be able to go up to 1 lakh nanometer. That is 1 lakh x resolution. And one more characterization you will be often using is your transmission electron microscopy. So unlike scanning electron microscopy, where the electron beam falls only on the surface of the sample, in the transmission electron microscopy, the electrons will get transmitted through the sample. Okay, so you have to understand that electrons are getting transmitted through the sample. So when the electrons are getting transmitted through the sample, whether if the sample is going to be thick, like it is going to be more than some 10 microns, will it allow the electron to pass through the sample? No, it won't allow the electron to pass through the sample. So the electrons will just stay on the surface and you will get just a opaque image on the screen. So when you are taking your sample, for example, a nano fiber or a quantum dot or a graphene structure, okay, you have to ensure that the sample is as thin as possible. Whenever the sample is very thin, you will be able to get wonderful transmission electron microscopy images. When the the electrons from the TEM passes through your sample. If it is going to be a sample from a biopsy sample from a pathologist, again here the sample preparation is very trivial. You have to be very careful in creating a proper block for the sample. You have to embed the sample properly, fix it. You have to make very thin slices, and you are going to place your sample in the stage of the electron microscope, and then the electron beam is going to pass through your sample and ensure that again the samples are conducting. Only in the conducting samples the electrons will pass through. Otherwise the electron will get charged over the surface of the sample, and it may even destroy or damage your sample because of the heat which is generating on the surface of the sample. Okay, so whenever you are using polymeric sample or this organic kind of sample in your electron microscopy, this high intensity electron beam can create heat in the surface of your sample. So this heat, sometimes the polymers may get even melted inside the chamber, or the images which you are getting may be false because of the samples getting melted. So all these things should be taken care when you are preparing a sample for the electron microscopy images. So both in scanning electron microscopy and the transmission electron microscopy, you will be able to get the images. There is just the photographs, the magnified photographs of your sample, and also along with that you will be able to get the elemental composition of these sample, because these how we are getting the elemental composition is these electrons, when it interact with your sample, it will generate X-rays from the valence bands of the atoms. That is uh, the electron levels, the K level, L level. You would have studied the chemistry, right? So in these valence bands, the electrons will fall and it will generate X-rays coming as a secondary rays coming out of your sample. So when these X-rays are detected, it can particularly identify what kind of atom is generating that X-ray. So you will be able to find the elemental composition, but the elemental composition that you are getting from a electron microscopy is not the final composition. There will be always error in the elemental composition. So coming to the elemental composition, I will be discussing other methods to find the elemental composition. And of course, you can get the elemental composition from the scanning electron microscopy from the EDS pattern. Okay, there is energy dispersive spectrum which you can obtain from these images, where you can get the elemental composition. And then other than that, in some papers you would have also find some patterns which I have shown in the screen, that these dot things. So what are these dot things? These dots are nothing but the diffraction pattern. When the electron interacts with your sample, it will cause a diffraction image. Similarly, what I explained in your X-ray diffraction, in your electron microscopy also you will get a diffraction pattern. So this is the diffraction pattern which you are getting in this getting as an image. And with this diffraction pattern also, you will be able to analyze the crystal structure. So if it is a metallic sample, 100% you will be able to get this kind of diffraction pattern. So with this diffraction pattern, you can analyze what is the spacing of each crystal plane. So what that metal is, if there is any impurity in the metal, what is that impurity, how much percentage of that impurity is. So all these can be identified with this SAED pattern, which can be generated from the transmission electron microscopy. So coming to the elemental composition, I was talking about elemental composition in your electron microscopy. So the electron microscopy can only give you a arbitrary number, like how much may be the composition, and it can find what are all the elements that can be present in your sample. But to get a confirmatory, both a qualitative and a quantitative value for your elemental composition, you have to do ICP. that is inductively coupled plasma spectroscopy. So this is a high sophisticated mission, and here a high temperature plasma is involved in analyzing your sample. So first you have to, mostly liquid samples are preferred for this kind of analysis. So if you are having a powder sample also, you should be giving your sample uh, diluted or suspended in acidic solution, so that the sample will be finally in a ionic state. You have to convert your powder sample or a metallic sample, whatever you have in your hand, in an ionic state, suspend in a liquid, and then you have to give for analysis. So when you give this liquid sample for analysis, they will use a high temperature plasma to pass through your sample, and it will detect the ions which are suspended in the solution. So this method is a very, very highly sensitive method, so that you can identify exactly what kind of mineral or ion is present in your solution. Like many of your research will require the ion release. So you may be using various types of ions in your research, like strontium, silver. For antibacterial activity, you may be adding silver in your material, strontium, magnesium, whatever it is. When you are going to find the ion release, or you may be also studying the degradation property of your material, like when you are incubating your material in artificial saliva, how the material is degrading, how much percentage of ion is getting leached out of your sample. So for these kinds of studies, you may be using this ICP method to find how much percentage of ion is getting leached out from your sample at different time points. So you have to periodically collect the samples, and you have to take it in an ionic solution form. Maybe you may make it ionic by, as I said, you may add acids to make it even more ionic, and then you have to give the samples to the lab. So usually the ppm level of the ions in the liquid is easily found by this method. So we have covered about X-ray diffraction, the spectroscopy, and then the elemental analysis and the morphological analysis. So all these things can be easily covered. To start with any material, you want to do a elemental analysis, or you have to identify the material. You have to identify the morphology of the material. These three or four techniques which I have discussed till now is enough for you. If you want other kinds of characterization, like you want to find out the mechanical property, how your material is going to behave at different temperatures, like your our oral cavity is a very vibrant environment which has a temperature fluctuation. So if you want to identify how the material will react at different temperature, you have to go for other types of analysis, like thermogravimetry analysis. So in the thermogravimetry analysis, you have to just take a pinch of material. You will be subjecting the material to a high temperature which goes up to 1000 degrees in a nitrogen atmosphere. Why nitrogen atmosphere? Because your samples, either it will be a polymer or a composite, whatever it is, it will start reacting at higher temperature with the atmospheric gases. So to avoid that reaction, you have to always maintain the sample at a nitrogen atmosphere. The lab will help you in doing that. The lab where you are going to give your sample for this TGA will help you in doing that. So they will have a nitrogen atmosphere in which your polymer sample, you can give your polymer sample to them. They will heat it to up to 1000 degree. They will calculate the weight loss happening for your sample at different temperature, and they will give you the results. And based on the weight loss at different temperature, you can identify what kind of substance would have got evaporated from your sample, and what would be the percentage weight of that material in your sample at that particular temperature. So you have, with the help of the graph which you are going to get from the lab, you will be able to do that. Like for example, till 200 degrees Celsius, only volatile components in your polymer sample will get evaporated, like any solvents which you are adding, like acetone or ethanol or whatever it is, which might have get trapped in your sample would have get evaporated till 200 degrees Celsius. from 200 to 600 degrees Celsius, your polymeric sample will get degraded. Okay. And then you will have weight loss. And then above 400 degrees Celsius, your carbon itself will get degraded. And then finally, only the ashes or the ceramic material, that is the calcium carbonate or calcium oxide will finally remain, and the silica will remain. So like that, you can easily identify what how your material is reacting at that particular temperature, and you can find how much would be the volatile component, how much is the polymer component in your material. So this is a very useful material when you are especially using polymers in your sample. And then UV spectroscopy. So who all are working on drug delivery and some kind of ion release studies, you all should have used UV spectroscopy in your research, and or you will be needing UV spectroscopy in your research. So UV spectroscopy is something similar to FTIR spectroscopy. So in FTIR, you will be using the infrared spectrum. Here you are using the ultraviolet spectrum. So ultraviolet spectrum will have the wavelengths from 200 to 400 nanometers. In most of our drugs or the molecules in the drugs can absorb the wavelength from 200 to 400 nanometer, and it can give it can absorb, and it can allow the UV rays to pass through the sample, and the remaining UV rays which are passed through the samples can be measured in the UV spectroscopy. So for this UV spectroscopy, you will be asked to give a liquid sample. The solid sample cannot be used for UV spectroscopy. Only liquid samples can be used. And the UV spectroscopy, this is also a very easily available instrument everywhere. All the analytical labs will be having this instrument for you. And so you will be having a glass cuvette in which you will be having your drug release sample or ion release sample. From your research papers, you have to find for your particular drug what is the particular wavelength it is going to maximum absorb. So that thing you have to find out from the research which are already published, or from the library which are existing from the material supplier. So you have to find out that, and then you have to pass that particular wavelength light to your sample. Your sample will absorb that particular light at that particular wavelength, and it will also allow some light to get passed through the sample. Okay, so based on that, how much it is absorbed, how much it has allowed to pass through the sample, you will get an idea how much has got absorbed by your sample. So based on the absorption, you will be able to calculate the concentration of the drug in your sample. So this is a very, very simple technique anyone can use in your drug release studies. And then you have particle size analyzer. So nowadays, many of our researchers are very much focused on nanomaterials, because nanomaterials can have a very good uh, uh, very good drug release properties, very good tissue engineering properties, because of its high surface area, and there are a lot of applications for the nanomaterials for imaging those things. So when you are particularly focusing on nanomaterials, you have to use the particle size analyzer to prove that your particle which you have prepared falls in that particular band of particle size. Like usually a nanomaterial will be around some 0.1 nanometer to 10 nanometer. Or if it is a micron material, it will be from 100 nanometer to 10 microns. So that will be the particle size distribution. There are two types of particle size analyzer. One particle size analyzer is dynamic light scattering method. So this it's called as DLS also. Okay, dynamic light scattering, which is called as DLS. So in this method, we use the principle of this apparatus use the Brownian motion of the nanoparticle. You know what is Brownian motion, right? You all must have learned in your schools. So when a lightweight particle is suspended in air or in water, okay, it will be just floating in the air, or it will be just floating in the water. Okay, so that's called as the Brownian motion. So when the light passes through this particles which are suspended in the air, you will be able to see that fine dust which is just floating in the air. So that's called as the Brownian motion. So based on this Brownian motion, this particle size analyzer, that the DLS apparatus, use this Brownian motion principle, and it can able to identify the particles which are particularly measuring between 0.6 nanometer to 6 micrometer. Okay. So if you are very sure that if your material is compulsorily nano in size, that is only around 10 nanometer or 20 nanometer, you have to go for DLS method. Okay. There is also another particle size analyzer which is called as laser diffraction analyzer, which uses a laser light. So there it can identify the particles which is above 10 nanometers, that is in the micron range, above 10 nanometers to up to 3 mm. So that is comparatively a larger particles. You have to use laser diffraction analysis. So these are the two particle size analyzer which are generally existing in our labs. So when you choose which kind of analysis you need, you have to first have an idea what kind of particle it is. So if you are not getting a result in DLS, you may of course get a result in laser diffraction analysis because your particle may be in micron size. So you have to know about this. And then for getting a good particle size analysis result, always you have to suspend your nanoparticle so that it is not getting agglomerated, because your nanoparticles will have a high surface energy. It can attract the particles adjacent to it, and it can form as a it can be seen as a micron size particle. You have to disassemble this nanoparticle to see the true particle size. For that, you may have to use ultrasound vibrations to disperse this agglomerated particles and to get the exact particle size. And here the concentration of the solution, what you are going to keep in the apparatus also is important. If the concentration of the solution is too high, you may not get a good Gaussian curve. Actually, the result of this DLS will be a Gaussian curve. You may see the distribution of the particle size. So if you are having a very much saturated solution, the Gaussian curve may not be very good, and then you will get erratic results showing that your because your samples are getting agglomerated. So yeah, ideal concentration should be used for doing this analysis. So next I will be talking about mechanical testing. So mechanical testing, we dentists are usually strong in mechanical testing, since our UG portion itself covers most of the mechanical testing what is needed for a dental material. So so if you are developing a material for a dental implant, or if you are developing a material for a prosthetic crown, for orthodontic wires, these kinds of mechanical testing is very important. You have to test impact. Have to test you have to test impact, fatigue, creep, the bending of the materials, and of course the tensile, compressive, and flexural strength of the material. So mechanical testing facilities are available throughout India in different labs, and it is very easy to get access through to these kinds of instruments, and it is also very cost effective to find these kinds of mechanical testings. And the only thing I wanted to tell in the mechanical testing is the sample preparation matters a lot when you are doing for a mechanical testing. How we are going to mount the sample. You may need to sometimes mount the sample in a resin, or you maybe need to give the sample in a particular size and shape to get a good result. So there are different types of, like, if you may be reading the pull-out strength of the implant. So you may have to give you may be giving an in vivo sample where the implant has got osteointegrated in the bone. Okay, so you may be finding the pull-out strength of the implant from the bone. So how well you are mounting the sample in the resin, how we are going to fit the sample in the mechanical testing instrument, all these matters. You have as a dental researcher, you have to discuss with the particular technician who is going to handle that instrument, how the assembly of the instrument is. Based on the assembly of the instrument, it is very, very vital to mount the sample accordingly and to place the sample and do the testing. The results are all straightforward in your mechanical testing. We as a dentist will very easily understand how the how the results is how to interpret the results in relation to your sample. So you can't be blindly giving a sample to a technician. You have to sit and guide him how the sample is going to be mounted to get a exact value when you are testing. And next, I will be talking about contact angle. So we all are talking about mostly the biological tissues and the biological samples, and of course the biomaterials. So when we are talking about biomaterials, one characterization which we often miss is the contact angle of the material. So why this contact angle is important? You have to find out whether the sample is hydrophilic. Hydrophilic is what? Water liking, or whether it is hydrophobic. That is, it doesn't like water. Okay, you have to find out that when you are developing a dental implant, or when you are what to say, when you are developing a composite cement. Okay, for example, first I will take a titanium implant. The osteo integrating surface, you are doing some surface coating. You have to check whether the surface coating you are doing to the dental implant, whether it increases the contact angle or decreases the contact angle. This is very important, because if the contact angle is going to be very high, okay, your cells are not going to get adhere to your sample. It is just going to be away from your sample. Only if the contact angle of your implant is low, the osteointegration is going to happen. Otherwise, there is not going to be any osteointegration at all. So the contact angle is very important when you are developing any material which is going to be in contact with the biological tissues, especially. Okay, unlike these implants, for example, a crown. Okay, for example, a zirconia crown. There you may not, you don't need a low contact angle, because you don't need the bacteria or your dental film, the biofilm, or the plaque. You don't want the plaque to get accumulated on your zirconia crown. So there you need a high contact angle. So this contact angle is very important when you are especially working on materials which are going to be in the biological interface. Okay, so and with the help of contact angle, you will be also able to identify what is the surface energy of the sample. A high contact angle sample will have low surface energy. That's why your cells are not going to get adhered to your sample. And the low contact angle sample will have high surface energy. So the cells will like it. The biological tissues and the cells will like it, and it is going to get adhered to your sample. And based on this contact angle, how the lipids are going to get settled in your sample, everything will be affected. Like you may be having a drug releasing medium, which what to say, like you are developing a tissue engineering scaffold, for example. You want to bind it with some drugs. There also the contact angle matters. So your tissue engineering scaffold should have a high surface energy, so that it should allow the molecules, the low molecular weight molecules in the drugs to get adhered to your tissue engineering scaffold. So for these things, contact angle should be studied when you are developing these materials. And many of you, for your materials, you would have also needed porosity measurements. So porosity measurements especially is needed when you are developing a tissue engineering scaffold, for example, for periodontal applications, or in maxillofacial reconstructions. You are developing a tissue engineering scaffold with some polymer and hydroxyapatite or bioglass or whatever it is. There all you will be needing to know the porosity of your scaffold. So you have to identify what is the exact pore diameter. You have to identify the pore volume of your scaffold. You may need to understand the surface area where the cells are going to get get bind to the scaffold. And you have to also understand the interconnectivity of the porosity inside your tissue engineering scaffold. So there, in these kinds of studies, porosimeter is very important. Usually in India, mercury porosimeter is easily available in various labs. Mercury porosimeter is available. So why they are using mercury is it is a non-wetting liquid. So it can be easily passed through your sample under high pressure. So based on the amount of mercury which is getting injected into your porous sample at different pressures, you will be able to find how is the porosity distribution in your sample, like how much pores are big, how much pores are above some 300 microns, how much pores are below some 200 microns. Like that, you will be able to get an idea, okay, how the porosity is getting distributed in your sample, and also you will be also getting the volume of the porosity. So just I want to conclude with this slide. Like where all you will need these characterizations, when all these characterization techniques. I have not completed what are all the characterizations you may need, because it's endless. So many newer instruments are coming up every day. Even nowadays people are using microcomputer tomography, nanocomputer tomography, surface topography measurements, like that. Different instruments are coming every day. And then you have AFM, you have nano indentation, which can give very fine mechanical measurements of your material. So a lot of characterization techniques are available. It is up to you to understand what characterization technique will suit for your material. Okay, it is you to decide how we are going to study the material, and how we are going to take it to next steps. Okay, with what characterization you are going to start, how we are going to study finer and finer. So it is up to the student to decide what is the technique which you will need. Okay, so as I said, tissue engineering, if you are going to develop newer materials for tissue engineering, like for example in periodontology, in maxillofacial surgery, or in endodontics, there all you will need a lot of characterization, starting from X-ray diffraction, FTR, ICP, everything you will be needing to use. If you are using it, if you are going to do a drug delivery study, of course you will be using UV spectroscopy. If you are going to do a surface coating study, you may be using scanning electron microscopy to find out how the surface coating has got deposited, what is the morphology of the surface coating, what is the thickness of the surface coating. All these can be, for these kinds of morphological analysis, you may be asked to use the scanning electron microscopy. If you are going to use, if you are developing a material for imaging, you may be using FTR, you may be using UV spectroscopy again. If you are developing a material for prosthetics, if you are developing a material for orthodontics, there all you will be using the mechanical characterization a lot. So in all these fields, you will be needing the analytical techniques, and you have to find, like, if your material is crystalline or amorphous or organic or inorganic. Based on the material characterization, it is up to you to decide what characterization technique will be suitable for your material.